In our previous video, we learned how to solve for capital A sub n values that now include not only the planform and the washout, but also the aileron and the rolling rate. And so our next question then would be, well, what is the resulting rolling moment? We can integrate lift, for example, to get a total lift coefficient. We already know how to do that. We can integrate in order to get an induced drag, and we'll go over that a little bit later again. But we're also interested in the actual rolling moment due to this aileron deflection and rolling rate. And so the way we do that, so after we've computed these little a, n, b, n, c, n, and d, n terms, we can plug them into this equation here, multiplied by these magnitudes, so the magnitude of, or the washout amount, the aileron deflection, and the rolling rate. That gives us capital A sub n. That A sub n gets plugged in here to capital gamma to give us our vorticity distribution along the wing, which is related to the lift. So now we can compute the lift distribution along the wing. So let's look at this analytically. Actually, it turns out that we can now look at or find the rolling moment analytically from this solution. So let's start here by defining the rolling moment, and we're going to look at the rolling moment coefficient on the wing, and that's equal to the rolling moment L. Remember, we give that the symbol L, divided by 1/2 rho v infinity squared times an area times the wingspan. So this is how we non-dimensionalize a rolling moment and get a rolling moment coefficient. Now the rolling moment L, I'll write up here, L is equal to the integral of the lift from minus b halves to b halves. So we're going across the entire wing. We're integrating the lift at any z location times the distance to that location z, and we're integrating in z. Okay, so I'm not going to work through the math, but you can basically, we can plug this relationship in here where gamma is a function of z comes from that equation there. So we can take that information and plug it into, well, right into this lift distribution and integrate, and we end up with an integral of summation of these sine terms over here. And the nice thing about that, again, the nice thing about working in this Fourier sine series is that many of those terms drop out. In fact, all of the terms, all of the an terms drop out of this integral except for the second term. And we find out that the rolling moment coefficient, you can write that as minus pi ra over 4 times a2. Now that's pretty incredible. Because you can imagine that this math can get a little bit hairy, plugging this into this equation and then taking the integral of that of this infinite sine series, and it just turns out that which is one of the benefits of using these sine series, is that terms drop away, and we're left with just the only term that affects our rolling moment is a2. Okay, so we can we know that capital A sub 2 from this equation up here is related to all of our little a's and b's and c's and d's. So let's just write that out here really quickly. So minus pi ra over 4 times little a sub n times alpha minus alpha L0 at the root. And what I meant to write there is little a sub 2. We're only looking at the second term, minus b sub 2 times capital omega plus c sub 2 times delta a plus d sub 2 times p bar. Okay, so this is how now the rolling moment is related to our little Fourier coefficients, or our decomposed Fourier coefficients. Well, it turns out that for a symmetric distribution, anytime you have a symmetric distribution in, let me scroll back up here, in this term right here, so alpha z minus alpha L0 z, so our twist distribution, anytime that's symmetric, the even terms are equal to 0 and the odd terms are non-zero. And so if we constrain ourselves to a symmetric planform, which most aircraft are, okay, if we say we're going to use a symmetric planform and constrain ourselves to a symmetric washout, which again is very common, then that means that that A2 and B2 are both 0 because those are even terms, and all of the even terms, in fact, AN and BN equals 0 for N is even. All of the even terms drop out, and therefore obviously A2 and B2 are 0 as well. So if that's the case, then our rolling moment coefficient can be simplified to simply be minus pi RA over 4 times C2 times delta A plus D2 times P bar. And we actually prefer to rewrite these coefficients in terms of derivatives with things. So we would say the rolling moment coefficient is the change in rolling moment with respect to delta A times delta A plus the change in rolling moment with respect to P bar times P bar, where the change in rolling moment with respect to delta A is just minus pi RA over 4 times C2, and the change in rolling moment with respect to P bar is equal to minus pi RA over 4 times D2. Okay, so all I've done is rewritten this equation in a different form here, where I've taken everything proportional to delta A and turned it into this coefficient, this change in rolling moment with respect to delta A. This is what we call a control derivative. So this is this tells us how much aileron deflection we need per unit of per unit change in rolling moment coefficient. Okay, so this basically tells us how strong our ailerons are, how much rolling moment they can create. So it's a change in our rolling moment coefficient with respect to delta A times delta A, and then again this is a derivative telling us how strong P bar is at controlling, or how much it affects our rolling moment. And again, it just comes from D2 times this stuff out front. That's that coefficient there. So this is our resulting rolling moment, and that's one of the the reason that we deflected the aileron in the first place is to create a rolling moment, and that creates a rolling rate. And now we've accounted for both the rolling moment, or the aileron and the rolling rate, and how those affect our rolling moment. And it all comes down to just the second Fourier coefficient, pretty amazingly. It only depends on the second one. And if we assume that we're working with a symmetric planform and symmetric washout, which most of the time we are, then those terms drop out, and we're left with just C2 and D2 that affect the rolling moment. And those are related to the design of our aileron. C2 is related to the design of our aileron from this equation up here. Remember, that's from our aileron distribution, and D2 is related to just this linear change in angle of attack as we go out for rolling rate.